Hello calculus fans, and welcome to section 3.5 where we look at implicit differentiation. So far the function we've been working with can be described by expressing one variable explicitly in terms of another variable. For example, we have y equals, we've got this one variable y expressed in terms of x, right? There's all x's over here. And like this one too. These are the functions that we're used to seeing. We're used to seeing one variable expressed explicitly in terms of another variable. But some functions are defined implicitly by a relation between x and y. And we've seen some of these also. We've seen the equation of a circle like this, right? Equation of a circle centered at the origin with a radius of 5. Or maybe something like this. Well, let's look at this one first. So we are able to work with this one, right? If we were going to graph that in a graphing calculator, we would say, well, we could solve this for y. We could say y squared equals 25 minus x squared. And then we could say y equals, we could take the square root of each side and get plus or minus the square root of 25 minus x squared. And if your graphing calculator is in function mode, you could graph the positive square root, then also the negative square root, put one of them in y1, one in y2, when you'd have both sides of it. So you can write this explicitly as two explicit functions, right? Y equals the positive root and the negative root. So we could still work with this one. What about this one? You think this would be fun to solve for y? Well, you can ask, Wolfram Alpha or some equation solving software, and you'll see that this one is not a very pretty answer. Wolfram Alpha can solve it for y. And even this one, I asked Wolfram Alpha to solve this for y, and you get like a very not friendly looking answer. This one, however, it's impossible to find a similar expression for y in terms of x. It just doesn't exist. So does that mean that we are not going to be able to take derivatives of functions like this? Well, probably not the case, right? If it were the case, we wouldn't have section 3.5, and we wouldn't be talking about implicit differentiation. So we can answer this next question. Can we take the derivative of a function that is defined implicitly? Yes, we can. Or do we have to first solve the equation for y in terms of x? No, fortunately we don't. We are going to use the method of implicit differentiation to find the derivative of y without having to first solve the equation for y. This consists of differentiating both sides of the equation with respect to x, and then solving the result equation for y prime. The key is to remember that y is a function of x, so we must use the chain rule. We're going to be using the chain rule here whenever we encounter y. Okay, and I'll sort of explain this as we go because it's a little confusing at first. Okay, implicit differentiation will take a little bit of practice. So let's look at this first example. We'll start off with kind of an easier one. So we want to find dy dx if y squared equals x. So we're going to do this a couple of ways. Number one, we're going to do what we know we could do. We know we could solve this for y and get two expressions, right? So first, let's just think of it like this. Let's do this two ways. Number one, let's say we know that y equals plus and minus the square root of x, right? And that's just from taking this equation and take the square root of both sides, right? The square root of y squared is not y, it's the absolute value of y, right? And then so we get two answers there. And they are over here. We get the square root of x and also the negative square root of x. So what we could do is we could do it like this. We could say, let's let y1 equal the square root of x, and we'll let y2 equal negative square root of x. Okay? So then if we take the derivative of y1 with respect to x, so take the derivative of this. So remember, this is really x to the 1/2 power. X to the 1/2 power. So we use the power rule. So we get 1/2 x to the minus 1/2. Right? And we've seen this enough where you might sort of automatically write it like this now. So just in case. If I take the derivative of this, so derivative of y1 with respect to x, by the power rule I get 1/2 x to the minus 1/2, which of course is 1/2 times 1 over x to the positive 1/2. And then you just multiply straight across, and instead of the 1/2 power, write a radical. So we get here, okay? We could do the same thing with the derivative of y2 with respect to x, and we'll just get the same thing with a negative. We get negative 1 over 2 times the square root of x. Okay. We also want to think of this a different way, okay? So the second way, this is where we're headed. We're going to treat y as a differentiable function of x. So we're going to treat it sort of like it's an unknown function. We just know that it's a function of x, so the chain rule has to come in. So we've got y squared equals x, and then we'll do the power rule, and the chain rule will come in. So if I use the power rule and I go 2y to the 1, but y is not plain old x, right? Because I'm taking the derivative of y with respect to x. So it's not like this is x squared, it's y squared, right? So I take the derivative, I get 2y to the 1, but since y is not plain old x, now the chain rule comes in, and it says multiply by the derivative of y prime. Right, so I'm going to get 2y to the 1 times y prime, which already is dy dx, equals, and when I take the derivative of x, I just get 1. So the derivative of x is 1. So I'm basically differentiating both sides of the equation. And since y is a differentiable function of x, the chain rule comes in. Right? Power rule says 2 times y to the 1, because this goes down by 1. And then this is not plain old x, it's some function of x. So the chain rule says multiply now by the derivative of that y. So then if we wanted to solve for this derivative, dy dx, I'd divide each side by 2y. And I would get dy dx equals 1 divided by 2y. And if you think about these answers here, these are really the same as what I got over here. These are the same answers. Well, same as these, right? Because 2 times y, well, what's y? Well, y is equal to this, right? 1 over 2 times y is the same as these. So these are the same answers. And this is just an easy enough example where we can do it the way we've always done it before, as long as we split it up into 2 pieces, right? But we can see that these are equivalent here. And the part that we have to keep in mind is this. So since y is a function of x, we need to use the chain rule with y. We need to always use the chain rule when y is involved, because you can think of y as some unknown function of x. So if we were to do something like, let's take the derivative, let's think of it like this. Well, let me write a couple of these down here. Okay, so if I take the derivative of x with respect to x, I'm just going to get 1. I know this is just equal to 1. All right. If I take the derivative of x cubed with respect to x, it's just a power rule. This is equal to 3x squared. Right, and we're done. But what if I take the derivative with respect to x of y? Well, now basically y is some unknown function of x, so I'm basically just going to get y prime, or dy dx, but I'm going to write it as y prime, right? So that's just y prime. And if I have The same idea over here with y cubed. Well, look at how this time up here I had 3x squared. So that part will be similar. It's going to be 3y squared. So I'll write that down first. But in this case, we're not done because y is some unknown function of x. It's not plain old x. I'm differentiating with respect to x, and this is not plain old x. So now the chain rule says multiply by the derivative of that. So now I have to multiply this by y prime or dy dx. Okay, so what about, with those examples in mind, what if we have the derivative of sine of x? Pretty easy, right? Derivative of sine of x, cosine of x. Okay, what about this though? The derivative of sine of y. Well, the derivative sine of anything at all is cosine of that same anything, but this anything is not plain old x. I'm differentiating with respect to x, and I have an unknown function of x. So the chain rule is basically saying that is not x. We need to consider the rate of change of that function, whatever that function is. So I have to multiply by y prime. So basically, whenever we have a y involved here, we're going to need to use the chain rule with that y. And this is a kind of a typical problem that we'll find. I've been kind of using both. Remember, dy dx is the same as y prime. You can use whichever one you want. Sometimes this one is sort of bulky to use, but then y prime sometimes can be confusing because it might look a little bit like y to the first power. So you can use whichever one you want. I typically use y prime just because it's not quite as bulky as this, but it's totally up to you. So if I'm going to differentiate here, I'm going to take the derivative of this whole thing with respect to x. Well, remember, I don't have to try to solve this for y. This would not be easy to solve for y because y is the argument to the sine function and it's also over here. But I can just differentiate straight across, just like this is. Just remember, I'm differentiating with respect to x. So while this will just be 2x, this and this will both involve the chain rule, right? Because there's these functions of x. Y is an unknown function of x, right? So if I go ahead and differentiate, I'm going to get 2 times y prime, right? The derivative of y is y prime equals 2x. Nothing new to see here. This is just the derivative of x squared is 2x. Now here again, 2 goes along for the ride. The derivative of y is just y prime, or dy dx if you prefer. Over here I take the derivative of sine of y. Well, that's just going to be cosine of y, but this is not plain old x. So the chain rule says multiply by the derivative of that thing. Okay, so remember, we are looking for dy dx, or y prime. So basically from here what I need to do is get all the y primes on one side of the equal sign. So this term here I'm just going to have to subtract. I'm going to subtract cosine y times y prime from each side of this equal sign. So I subtract it from here. Well, I guess I'll just do it like this, just to make it really clear what we're doing. We're going to subtract this from each side of the equal sign. So that's gone. So we get 2y prime minus cosine of y times y prime equals 2x. And of course, if we're going to solve for y prime, we're going to want to factor y prime out. And this will be pretty standard with this type of problem. You differentiate everything with respect to x, then you get all the y primes on one side of the equal sign. And then you factor out a y prime because we're solving for y prime. So I factor out this y prime, and I get 2 minus cosine of y equals 2x. And then since I want to get y prime by itself, I have to divide each side by 2 minus cosine of y. And then that will cancel. So you get y prime equals 2x over 2 minus the cosine of y. Or dy dx if you prefer. So dy dx, or y prime, is equal to 2x over 2 minus the cosine of y. All right, example 3, as you can see, is a very nice looking problem. So I was thinking you guys should try this one first, okay? But I want to give you a heads up on part of it. Right here we do have the product rule, right? This is the product rule. This x times, treat y like some unknown function of x, okay? So it's x times some unknown function of x. So we're going to need the product rule here. So what you should do is try this one out, differentiate straight across with respect to x, then get all the y primes on one side of the equal sign, it doesn't matter which, and then factor out a y prime, and then divide to get y prime isolated. So try it out and then check back. Okay, hopefully you're back from trying out the problem. And let's take a look. So looking at this first part here, I'm going to do the product rule. I'm going to do it the kind of the easy way, I guess. I'm going to write it down twice, take turns with the derivative. So I take the derivative of this first, then take the derivative of that. All right, then we've got plus. The derivative here is just the power rule. 2 comes down, so 2 times 2 is 4, y to the 1. So we have 4y to the first power, and then times, that's not plain old x, and we're differentiating with respect to x, so now I have the chain rule that says multiply by y prime. Equals, well, the derivative of x is 1, the derivative of y is y prime, right? And the reason these are different is because I'm differentiating with respect to x. The derivative of x with respect to x is 1. The derivative of y with respect to x is just dy dx, or y prime. Okay, so let's go through and finish these. The product rule here with the derivatives, well, x prime is just 1, so I don't really need anything there. 1 times y is just y. And then y prime, the derivative of y is just y, so it's just another y prime. Plus 4y times y prime equals 1 plus y prime. All right, so I need to get all the y primes on the same side. So I'm going to leave this over here on the left. I'm going to leave this on the left, but I'm going to move this one over. So I'm basically going to subtract y prime from each side. So once I do that, I'll have y plus x times y prime. That's a times. Plus 4y times y prime minus y prime equals 1. Right, so all I did, subtracted y prime from each side. So it's gone from here. So the only thing left on the right side is 1, and I moved it over here, so here it is. But now I've got this y that does not have a y prime factor, so I'm going to get rid of that one too. So I'm going to subtract y from each side now. So I'm going to get x times y prime plus 4y times y prime minus y prime equals 1 minus y. Okay, so all we've done, differentiated everything with respect to x, right? That's what we got here. Took 2 steps actually because of the product rule. Then all the y primes we put on the left side of the equal sign. Doesn't have to be on the left, we just had to pick a side. So it was easier in this case, put them all on the left. And then to get anything that doesn't have a y prime, I got that back over on the right. And now what we need to do, because we're going to solve for y prime, we need to factor a y prime out. It's in all 3 of these terms. So we factor y prime out, and we get x plus 4y minus 1 equals 1 minus y, right? You can always check. If I distribute this back through, I should get back where we were. And then from here, I just want to get y prime by itself, so I divide each side by this right here. So when we're all done, we get y prime equals 1 minus y over x plus 4y minus 1. And one thing that will happen sometimes, so over here I decided to put all the y primes on the left. I could have just as easily put them over on the right. So sometimes when you do that, you look in the back of the book, and maybe the textbook solutions manual went the other way. So what will happen sometimes is you'll notice that you get exactly the same thing, but every single sign is changed. And that's okay. Because isn't it true if I multiplied this, let's just say if I multiplied by -1 over -1, I'm still multiplying by 1, right? But wouldn't that have the effect of changing all these signs? Okay, so that will happen sometimes. Probably when you look in the back, you're checking your answers, and you'll see that you have everything exactly the same, but every sign changed. That means they're equivalent. That means your answer agrees with the answer in the back of the book. It's just from deciding to put y prime on the other side. Sometimes it will have the effect of basically changing all the signs. But remember, that's just like multiplying by 1 in the form of -1 over -1. Okay, now we've got one from the book. This is number 8 in both the 8th and the 9th edition of Stewart. So what we should do here is have you try it out. Remember, there's another product rule here. This one's a little tricky because there's a negative in front. So whatever happens to this product rule, this negative is going to have to distribute through. So give it a try. This one may take a few minutes, but give it a try and then check on back. All right, so let's take a look at this one. So we start differentiating with respect to x. Again, I'm going to use the y prime just because it's just less bulky to write. So we'll get 3x squared minus, this is what I'm going to do with this. I'm going to just leave this minus here and just sort of in brackets do this multiplication problem. Just to keep it simple, I don't want to worry about trying to distribute this negative through as we go. I'll wait till the end. So this is the product rule again, right? So we've got x times y squared plus x times y squared. And with the product rule, we go ahead and we take turns with the derivatives. Remember, the typical way this is taught is not this. It's the typical way would be first term times the derivative of the second term plus the second term times the derivative of the first term. Algebraically equivalent to this. This is just kind of an easier way to do it. But you can do it the other way also. And then here we're going to have the chain rule because we first had the power rule. So we go 3y squared, but that's not plain old x. So we need to multiply that by y prime. So we get plus 3y squared times y prime equals, I'm going to make a really common mistake right here. This happens all the time. A terrible mistake was made. Hopefully, you won't even be able to look at the computer screen. You'll be looking away because you don't like the look of it. What's the derivative of 1? It's not 1, is it? It's 0. Okay, so we take out our eraser, but it's a really easy mistake. It's easy to make that mistake, but remember, when you take the derivative of a constant, it's 0. Okay, so let's go through here. I'm going to finish this part up. So you get 3x squared minus, okay, x prime is just 1, so that's just 1 times y squared. Now, y squared prime is going to be 2 times y prime, right? Power rule says 2 times y to the 1, but then this y is not plain old x, so we need to multiply by y prime. Then we've got plus 3y squared times y prime equals 0. Now at this point, I'm going to clean this one up a little bit, just rearrange the terms, but I'm going to mainly just distribute the negative through. So we're going to get 3x squared minus y squared minus, now for this part I'm going to write 2xy times y prime, just because it's more standard to write it like that, plus 3y squared times y prime equals 0. So at this point, we need to get rid of, well, we need to keep the y primes on one side and get rid of everything else. So we can subtract 3x squared from each side. Maybe I'll do this one in steps. I'm going to go minus 3x squared from each side of the equal sign because I basically want to get rid of anything that does not have a y prime. Get rid of that. That gives me minus y squared minus 2xy times y prime plus 3y squared times y prime equals minus 3x squared. And now we need to get rid of this minus y squared because it doesn't have a y prime factor. So this time I'll go plus y squared on each side plus y squared. That'll be gone, so we get minus 2xy times y prime plus 3y squared times y prime equals, and just to not have a leading negative, I'm just going to go y squared minus 3x squared. All right, so now we've got all the y primes on one side, the y prime terms, right? Non-y prime terms on the other side. So now it's time to factor out a y prime. So if I factor out a y prime, I'll get negative 2xy plus 3y squared equals y squared minus 3x squared. And now finally, the last thing we need to do is divide each side of the equal sign by this thing to get rid of that. And once we do that, we get y prime equals y squared minus 3x squared over negative 2xy plus 3y squared. Okay, so hopefully that is what you got. We got some variation of it, some equivalent variation. Some of you guys may have put the 3y squared first, just again to make it positive. Some of you may have had the negative 3x squared plus y squared here. All those are fine. But I know you're probably thinking, sure would like to see one with an equation of a tangent line. Sometimes I'm a bit of a mind reader, as you know, and look at that. You're in luck. Who knew you were going to be so lucky today? Example 5, our final example says, find an equation of the tangent line to a circle at the point 3, 4. Okay, ultimately it's asking us to do something we've done 100 times before, equation of the tangent line. Well, basically that means our answer is going to be y equals mx plus b, right? Same as always, y equals mx plus b. And we do the same thing as we always do. Find the slope and then find b. Once we have that, we'll have the answer. So we want to find the equation of a tangent line to a circle. So we know what this looks like. This is circle centered at the origin with a radius of 5. We'll find an equation of a line to this circle at the point 3, 4. Okay, well, we need to find the slope, right? Isn't that what we always do in these problems? You find the slope. X squared plus y squared equals 25. And the slope, the easy way we have of finding the slope is we just find the derivative, right? And then plug in the x value that they're questioning, or that they're looking for. Now, in this case, we have a y value too, because this is implicitly defined, so we have x and y. But finding the slope is the same as always. We take the derivative, right? The slope is the geometric equivalent of the derivative. Remember, the derivative gives us a formula for the slope of the curve at any point. So we just need to find the derivative here. And now that we can find the derivative with implicit differentiation, we don't have to try solving for y. We can just do the derivative immediately right from here. So if I differentiate with respect to x, I'm going to get 2x plus 2y times y prime equals 0. Remember, y prime is going to give us the slope. So I'm going to subtract 2x from each side. Now I want to get y prime by itself. So what do I have to do? I have to divide by 2y. Right, that would cancel. So we get y prime equals negative 2x over 2y. Or in other words, y prime equals negative x over y. So here is the formula for the slope of a tangent line at any point. And we want to at this point 3, 4. X is 3, y is 4. So I just plug that in. So the slope that we're going to have is negative 3/4. So this is our slope. So we've got the slope, and now we just have to find b. So just like we've done a whole bunch of times before, we typically, the way I've been doing it is this way. But as some of you learned a different way, you can do it this way too. You can go y minus y1 equals the slope times x minus x1 if you prefer. If you do this method, you've got your x1, y1, right? You plug in your x1, and your y1, and the slope we just found out was -3/4, so that gets plugged in for m. And that method, when you plug these in and solve for y, you go right to the answer. Okay? This other method that we've been doing, mostly just because this is how most students learn this, is we plug in our slope here, and then we take that 0.34, and if our equation we're looking for is at this point, so in other words, this point satisfies our equation, that means I could take the 3, plug it in for x, take the 4, plug it in for y, and just solve. So I get 4 equals -3/4 times 3 plus b. So 4 equals -9/4 plus b. And keeping in mind that 4 really equals 16/4. Let me just rewrite this. To solve for b, I'm going to have to add 9/4 to each side. So if I add 9/4 to each side, I'll get 25/4 equals b. So now we know we have the slope and we have the y-intercept b, so our answer will be y equals -3/4 x plus 25/4. So that is the equation of a tangent line to this circle at the point 3,4. And for those of you who did it the other way works fine too. You can go y minus 4 equals -3/4 times x minus 3, or y minus 4 equals -3/4 x plus 9/4. And then over here to get y by itself, I would add 4, which is the same as adding 16/4. So I would end up with the same answer. Okay, and this is it's a little bit of a shorter section than it has been in the past because the 9th edition of Stewart changed 3.5 and 3.6 around a little, changed some of the information that was in 3.5 is now in 3.6. So section 3.5 is a little shorter. But from there you should be all set. And as you know, there's only one way to get better at these derivatives and at calculus in general. So go ahead and try section 3.5, implicit differentiation. Work hard, be persistent, and as always, if you have any questions, just let me know.